Hello students, in this video we're going to go over section 2.5 projectile motion. So projectile motion can be studied in terms of its rectangular components, which is what we're going to do in this section. So generally this is what a projectile motion will look like. Your particle will follow the path of this curve here. And here you'll have some initial velocity. I'll just write v sub 0 or v naught. And you can go ahead and take that velocity and break it down into its rectangular components. So you'll have the initial velocity in the x direction and then the initial velocity in the y direction. And you can do that for other points along this curve. So here you have another velocity, call that v sub 1. And you can go ahead and break that down into its horizontal and vertical components. Now we're going to neglect drag, curvature, and the rotation of the Earth because we're working with kinematics and not kinetics. So when we do that, the only force acting on the projectile is its weight. So this causes the projectile to have a constant downward acceleration. So I'm going to write a sub y, and this is going to be equal to negative g. And this is where g is equal to 9.81 meters per second squared, or g can be equal to 32.2 feet per second squared. And since we're ignoring drag and wind, etc., there's going to be no acceleration in the x direction. So we can write a sub x equals 0. And these here should be labeled. Make sure you label your axes. So now we want to come up with some equations for this projectile motion. So we're going to start with the kinematic equations from earlier on in this chapter. So I'm going to write those down. And since our acceleration is constant, I'm going to use these kinematic equations where we had s equals s naught plus v naught times t plus 1/2 a t squared. V equals v naught plus a times t, and v squared equals v naught squared plus 2a times s minus s naught. Since we have two components, we're going to use basically two sets of these equations, one for the x direction and then one for the y direction. So I'm going to do the x direction first. So looking at the first kinematic equation, I'm going to basically replace s with x. So the final x value is going to be equal to the initial x value plus the initial velocity in the x direction times t plus 1/2 a sub x, acceleration in the x direction, times t squared. But we already mentioned that this here is going to be equal to 0. So this is going to simplify to just x equals x naught plus v naught x times t. Now the other two kinematic equations aren't really telling us anything since the acceleration is 0. So basically all we would get from these other two kinematic equations is that the final velocity in the x direction is equal to the initial velocity in the x direction. So now we're going to look at the y direction. So for the first equation, we're going to have y equals y naught plus the initial velocity in the y direction times t plus 1/2 the acceleration in the y direction t squared. From the second kinematic equation, we're going to get that the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration in the y direction times t. And then the final kinematic equation tells us that the final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration in the y direction times y minus y naught. So this is basically how we derive from the kinematic equations we can use for projectile motion. So now we have some more equations. So for projectile motion, we'll have to analyze both directions.